the meantime, I'll get started over here. And what we're going to talk about today is we're going to start on the final module. So we're going to use mutual inhibition as a model of decision making, and we're going to go through some particular papers. There's one paper that we're going to be focusing on. I'll tell you in detail what that is. And we want to do it kind of like an illustration of the concepts that we've been talking about and kind of putting it all into play in the context of a particular neuroscience decision making. As such, we don't necessarily want you to learn a ton of details in this. It's more like we want you to kind of like see what the ideas are, get a sense of them, and play with it. And I mentioned already that during reading period, we'll be sending out an assignment with this. We'll be providing much of the code. We're not going to be asking you guys to write a lot of code. But the idea is that you should be able to play with these things. Okay, so that's what we're going to do. So I'll start today. I'm going to start by providing a little bit of background, kind of like why are we interested in this problem and where it comes from. So I'm going to start talking about decision making in general, and then I'll get to why are we looking at the particular network that we're looking at. And for decision making in general, when I talk about this, I usually like to start with this, which is what I call the most common behavioral observation in decision making, which is something that you guys experience in your daily lives. If you have a difficult decision to make, it takes you a long time to make up your mind. If you have an easy decision to make, you can do that really quickly. If you got accepted into 2 colleges and one is awful and one is awesome, you make up your mind really quickly. If you got accepted into Princeton, Harvard, and Stanford, then you're thinking, and it takes you longer to make up your mind. And that's been observed in a very wide variety of settings, anecdotally, as I said just now, in your daily lives, but also in the lab for a wide variety of different types of decisions, social decisions, sensory decisions. Those are the ones that we're going to be focusing on. Economic decisions, gambling decisions, memory decisions, what are you remembering? When you're searching in a visual scene, value-based decisions, for example, which ice cream do you prefer? All kinds of decisions. Basically, wherever people have looked, they've found this observation. So that's led to the idea that there's some common core process that underlies all of them. And this hypothesis sometimes goes under the name of noisy accumulation of evidence, or sometimes the particular model, one particular instantiation of the model, not the one that we're going to be looking at, but a variant goes under the name of the drift diffusion model, and there's tons and tons and tons of work using this model. So let me cartoon for you what this model looks like and what it does. So imagine that you're in a lab and you're a participant in an experiment where on each trial of the experiment, you're being presented with some stimulus and you're being asked to decide whether to orient to the left or to the right. That's your task on each trial. And now imagine that at the beginning of each trial, somewhere in your brain, we don't know exactly where, we don't know exactly how, that's one of the big research questions. There's a scalar variable, some abstract variable, that we're going to call the evidence accumulator A, just some scalar. Okay? And pretend that that scalar at the beginning of each trial has the value 0. And then as the trial unfolds, and you're looking at the stimulus, every time that you see something that makes you lean towards orienting to the right, towards deciding rightwards, you add a little something to that scalar A. And every time you see something that makes you lean towards deciding left, you subtract something from that scalar A. And then the idea is that when you get to the end of the stimulus, you just ask, what's the sign of A? If A was bigger than 0, you say, I'm orienting to the right. If A was less than 0, you say, I'm orienting to the left. Super simple picture, right? Extremely simple. But you can already see that it accounts for this observation. And the basic idea is that if the decision is difficult, if at each moment the evidence for right or for left is small, then the fluctuations that the things that you'll be adding and subtracting from A are going to be small, and it's going to take a long time to move away from this decision border. If you're near the decision border and things are noisy, it's difficult to say on which side you are. So it took a long time, and you didn't move far away. That makes it a hard decision because you're not sure which side of the decision border you're on. Whereas, if what you're adding, if at each moment the evidence for left or for right is really strong, then you're going to move far away from the decision border really quickly, and so that's going to be an easy and a fast decision. So super simple picture, accounts for a ton of behavioral data, so of course people love it, and it's been in the literature for about 50 years, used all over the place. There's a task that people started using in the mid-1990s and 1990s. Actually, the task is older, but the relationship to this accumulation picture started in 1996. And this is a task where subjects are presented with randomly moving dots. And what you can do is you can take a fraction of those dots and make them all move in the same direction. So if you have 0% of the dots that are moving in the same direction, then on each frame of the movie, each dot is moving in a totally new random direction, and you just see this jumble of motion. But if you have a lot of dots, for example, if 100% of the dots are moving in the same direction, then you'll see a very clear motion direction. And this is a stimulus that people use because by controlling the fraction of the dots, it was very easy to control how easy or how hard the decision was going to be. So you present the stimulus to the subject and you ask them, overall, do you see motion upwards or do you see motion downwards? Right? Or you could do it to the right or to the left, whichever two directions you like. And if you've got what's sometimes called 100% correlation or 100% coherence, sometimes the fraction of dots is referred to as coherence, then it's going to be a really easy trial. If you've got a very low coherence, then it's going to be a really hard trial. And the idea is that as you're accumulating evidence, say that that's the stimulus that you're looking at in the experiment that I described. In each moment, you're seeing the screen, you're seeing the motion of the dots. You're trying to decide whether to orient to the right or to the left, which way are the dots moving. And so on each trial, the trajectory of what you've added and what you've subtracted could be quite noisy. And that's what these thin lines here represent. But on average, across many trials, if you have a really weak stimulus, say these fainter colors, then the accumulator should rise slowly as you, on average, move away from the decision border slowly. Whereas for strong evidence, say 100% coherence, the accumulator should move away from the decision border much more quickly. Right? That's the general idea. And in 1996, two people, one of them had been at Stony Brook, but I think they had just moved to Stanford. So actually, these experiments I think happened in Stanford. In 1996, they were doing this kind of experiment with some monkeys. They were presenting monkeys with this random dots task. And they recorded from a particular area of the brain called lateral intraparietal cortex. I'm going to refer to it as PPC, or posterior parietal cortex for short. And what they saw there were firing rates of neurons that looked really similar to what this behavioral model had predicted. In other words, as the monkeys were looking at the stimulus, as they were making up their minds, perhaps deliberating as to which way to report their decision, they found firing rates of neurons. This is an average over many neurons, but it's not atypical, where the firing rates of the neurons, while the monkeys were forming their decision, ramped, and the slope of the ramp changed according to the strength of the stimulus. So for a weak stimulus, weak evidence, they ramped up slowly, but for strong evidence, they ramped up really quickly, exactly as this picture had predicted. And that was incredibly exciting because that model had come purely from behavior, no neuroscience about it. And now here were some signals inside the brain that looked a lot like what the model had predicted, suggesting that maybe indeed gradual accumulation of evidence is how the brain forms decisions. Now you'll notice that these traces, the slope of the ramp changes according to the strength of the stimulus, but you'll also notice that they end at different times according to the strength of the stimulus. And in this particular experiment, what they were doing was they were presenting the stimulus to the monkeys, and they were allowing the monkeys to make their choice, report either right or left, as soon as the monkey wanted. So the monkey made up its own mind as to when to report that. And in fact, in this model, there's one of the parts of the model is that if you hit a certain bound, if you've accumulated enough evidence for one choice or for another, that's when you commit to that decision, and that's when you admit the decision. So that means that for weak evidence, for difficult trials, it might take you a long time to reach the bound, but for easy trials, you would reach the bound much faster. So this model accounts for that. And in fact, if you fit the model, if you fit parameters of this model to behavior, so say as a function of the strength of the stimulus, you're fitting how often does the subject correctly report what the direction of motion was. And this is something that's called a psychometric function. When you fit these data, that gives you the parameters of the model. And now you can say, well, what does the model predict as to when subjects would produce their report? What they call reaction time. So the plot that I'm showing you on the right is not a fit to the data. This is what the fit on the left predicts about the data on the right. And you can see that the line, that's the model, it fits it really well. So the model makes predictions that are really pretty good and that are quantitative, both about the fraction of correct choices, the psychometric curve, and the reaction time, the time it takes to make a choice. This is the chronometric curve. Super simple decisions, right? It's just random dots. One of the remarkable things in this literature is how the effects that are seen in these very simple sensory or perceptual decisions, as they're called, often also apply to more complicated decisions. So for example, there are papers in marketing journals where people are literally deciding between buying cars, and you see some very similar effects. So even though these people are working with extremely simple decisions, the hope is that they might apply to more complicated decision making. So all of this is very nice, and I already told you that there's at least one region of the brain where you see signals that look like what the model had predicted. It turns out, now many years later, we know that there are many regions of the brain where you see similar signals, and exactly which regions are involved and which are important for the process, that's one of the questions that people are addressing. But what I haven't told you anything about, and nobody knew anything about, was how is it that neural circuits could organize themselves in order to produce signals like these. And that's what we're going to be looking at. We're going to be looking at a model of a neural circuit that produces signals like these. So what the model tries to do is reproduce firing rates that look like this, the ramping firing rates. And it tries to reproduce the psychometric curve and the chronometric curve. And the basic features that we're looking for is you have control over the strength of the stimulus, and the stronger the stimulus, the easier the decision, the higher the fraction correct. Makes sense? And in addition, the stronger the stimulus, the shorter the reaction time. Right? Those are the key features that we're going to be looking for. So how do you organize neurons from what we know, simple models of neurons? How do we connect them to each other? How do we make a circuit that would produce something like this? There's one more thing about the experimental data that I want to tell you that this model also reproduces, which is that if you make estimates, the subjects say, and I should point out the data that I was showing you over here, this behavior data, you find things like this with both humans and monkeys. So it's not just some crazy monkeys in a particular lab. This is a fairly general phenomenon. In particular, as you're looking at the stimulus, it takes humans and monkeys typically about 500 milliseconds to a second to make their decision. And during that time, you can try to make estimates as to which parts of the stimulus had a greater influence on the decision. Okay? And right now, in this plot, I'm not showing you how they computed this, but I'm just going to point out that roughly, these are very noisy, the red line and the blue line are more separate at the beginning of the stimulus than at the end of the stimulus. And I'm not telling you why this means the following, but that turns out to be evidence in favor of the idea that subjects weight the stimulus, the early part of the stimulus, more than the later part of the stimulus. The difference between the red and blue lines is an estimate of how strong the stimulus at that point in time mattered for the decision. So the fact that they're separate here but less separate here means early part of the stimulus had a bigger influence on the decision than the later part of the stimulus. And that's also something that we're going to be looking at. I am pointing out that we see this effect of what's called primacy, the early part of the stimulus mattering more than the later part. In this task, it turns out that in other tasks, more modern tasks that people have done, this doesn't turn out to be the case. So this is not, this thing that I'm showing you right here is not necessarily a general phenomenon. Nevertheless, let's start thinking about how we might make a model to do this. So this is the particular paper that we're going to be working with. So if you want to look it up, these are the authors, this is the reference. There's very similar kinds of plots to what we're going to be doing in another paper that's from my group, but really this is the one that we're going to be doing today. This one is about similar things, but slightly different work. So this is the one to focus on. So the idea in this model is that they're going to build it with two populations of neurons that are going to represent the two possible decision outcomes. And the idea is that when one population of neurons fires a lot, that will mean, oh, decision A, for example, go to the left. Whereas when the other population of neurons fires a lot, that would mean decision B. So these are the two options. And the way they set it up was having big pools of these two neurons. Here they're labeled as 1 and 2. And also having a lot of inhibitory neurons in that network that feed back onto all the other neurons. And it turns out that if you look through the math of this, so when they first set up the model, they set it up with 7,200 neurons, and each neuron was a spiking neuron in the model, so you have 7,200 voltages that you're keeping track of. But all of the neurons in the blue group, group 1 for decision 1, were really pretty similar. And all of the neurons in the red group, group 2 for decision 2, were also similar within that group. And these were receiving excitation from all of them and providing inhibitory feedback to all of them. So it turns out that you can average across, not across the pools of neurons, sorry, within a pool of neurons to simplify the equations. And you can simplify the effect of these inhibitory neurons into a model that looks more like this. And this model has only 2 variables, which is really nice. It's easy to plot. So we can do quiver plots. We can do the kinds of things that we've been doing in class. And so in this simplified model, and that's what we're going to be looking at, again, you have the 2 pools of neurons. But now each pool of neuron is just one variable. And that variable is going to represent the firing rate of that pool of neurons. You have the 2 pools of neurons. And again, you want one of them to be firing a lot. By the end of the trial, you want one of them to be firing a lot and the other one not to be firing a lot, right? Because it's the difference between the firing rates of those two. Which one is firing a lot tells you which was the decision outcome on a particular trial. If both pools of neurons are firing a lot, then it's like the system couldn't make up its mind. Right? But in this particular type of experiment, the subjects are told you have to make up your mind. They're called 2 alternative first choice experiments. And so you need to have one of the pools right. So the typical way in which people set something like that up is by having inhibition, mutual inhibition between the different pools. And this is a structure that is sometimes called winner-take-all. The idea is that if you make the inhibition strong enough, if one pool is firing a lot, it'll silence all the others, and so it kind of wins all the activity. And that's really what's leading to the decision-making dynamics, that only one of the 2 pools of neurons can be very active. Okay, so let me go back to iPad. So what exactly are the equations that we're going to be working with? Well, we want to use variables that represent pools of neurons. So we're not going to be working with spiking neurons. We're going to be working with what are called rate neurons. And each one of these is going to represent, as I said before, a pool of neurons. As always, please ask questions at any point. I'm already 20 minutes in and there hasn't been a single question. That's always a little disturbing. Oh well. Okay, so what are the differential equations that are going to govern our neurons? And let's say that R represents the firing rate of one of these neurons. By the way, I didn't post notes for this lecture yet. I'll post them after the lecture. I'll clean them up and post them. Sorry. I spent my time coding instead of writing the notes. But I hope you'll enjoy the coding. That's going to be the centerpiece of today. Okay, so the kinds of equations that we've looked at a lot at linear equations, but we mentioned that for neurons, we know that we need nonlinearities. Why? Because if we're looking at firing rates of a neuron, we know that firing rates can't go negative. Also, we know that neurons have refractory periods. Their spikes can't come too close together. So there's a maximum firing rate. So we want to put that in there somehow. And so the way that we're going to do it is in a way that many models use, not just this one. we're going to have equations that look like this. So first, we have a term minus r. So if we only had that, what would be the fixed point here for this single pool of neurons, for the single variable? If this were our only equation, what's the fixed point of these dynamics?
0.
And is it stable or unstable?
Stable.
Yes, because of the minus sign, right? Exactly. So this term just says, in the absence of any input, go back to 0. If there's no input, the pool of neurons stop firing. Because it goes back to its stable point, which is 0, which means a 0 firing. So let's add something that corresponds to the input, and we'll add a function of the input. Okay? And it's going to be a nonlinear function of the input, and we're going to make it a sigmoid function. And by that I mean something that has a shape like this. So the input is going to be some scalar, some total drive to the neuron, and the function of the input is going to be something that looks smooth and kind of S-shaped like this, with a maximum. The maximum represents the maximum firing rate of the neuron. We're just going to call that 1 for convenience. And this is going to be the minimum firing rate of the neuron. So we're going to make it 0 for convenience. Okay? And any function that has a shape like that would more or less do. A particular function that has a shape like that, and the one that we're actually going to use, is this. The hyperbolic tangent made positive. But the bottom line is simply that it's an S-shaped function like this. So adding that means that now our firing rates are limited to being between 0 and 1. Why is that? Okay. If you look at the equations themselves, there's nothing there that says that r has to be between 0 and 1. All that we've done is say that the f of the input has to be between 0 and 1. So what keeps us between 0 and 1? Well, imagine that r started between 0 and 1. And now let's think of what happens when the input is very large. So if the input is very, very large, then what's f going to go to? What's the value of f when the input is very large? When the input is way big, how much is f? 1. Right. So when the input is very big, this equation looks approximately like this, right? Because instead of f of input, we just have 1. Does that have a fixed point? And what's the fixed point? At what value of r does r dot equal 0? 1. And is that fixed point stable or unstable? Stable, exactly. Again, because of the minus sign, right? So when the input is very high, we have a new fixed point, which is 1, and we approach it. It's stable. If we were below 1, we're going to approach 1, but we're never going to go above it. Right? Whereas when the input is very negative, now f of the input is approximately 0, because now we're over here in this regime. And so now the equation looks like what we had written before, namely 0 is a stable point. We're going to approach that. Right? So if r starts between 0 and 1, it's never going to go outside of 0 and 1. So this is a way of bounding r in a way that is roughly inspired by what happens with neurons. Okay. So now we've got something that gives us no negative firing rates and a maximum firing rate, right? A maximum firing rate that we're going to call. And the structure of the network now is going to be something that has 2 variables, x and y. These are going to be our 2 dynamic variables, and they represent the 2 possible decisions. And we're going to have inhibition between them, and the little ball represents inhibition. And that's going to have some weight that I'm going to call WO. So the bigger WO, the stronger the mutual inhibition between these 2 nodes. And we're also going to have some self-excitation that I'm going to call WS for self. Okay. A little open thing here means excitation. And in addition, we're going to have inputs to the two nodes that I'm going to call Ix and Iy. So let's write down the differential equations that correspond to this. And once we've written down the differential equations, we have the dynamical system that we're going to be studying and playing with. So we're really taking the equations that we had over here, right? We're really taking this equation, but now saying, oh, we've got two neurons, so we've just got to do it for two of them. And so instead of calling them R, I'm going to call them X and Y. But it's basically the same equations. Right? So it's X dot is minus X plus F of the input. Okay, so how are we writing down the input to X? Well, it's got this Ix input, so I'm just going to write that down as is. So it's Ix plus some self-excitation. So I'm going to write that down as Ws times X. Right? So the stronger X, the higher the activity of X. Remember, X is going to be bounded between 0 and 1. If Ws is positive, then the stronger the input to itself. And we also have the mutual inhibition, right, which we're writing down as WO. Notice that we're making the system symmetric. The self-excitation for the X neuron is the same as the self-excitation for the Y neuron, and their mutual inhibition is also the same. So we're simplifying it that way. So I'm going to write it like this, WO times Y, with the caveat that WO will be negative. Okay. And WO being negative, that's what it's going to mean that it's an inhibitor connection. Okay, so that's our equation for X. And let's write down the same thing for Y. Essentially the same, except that now the input to Y is not I sub X, but it's I sub Y. And the self-feedback is not X, but it's now Y. And the mutual inhibition is not from Y, but is now from X. Those are our equations. Those are the things that we're playing. And once we've got these equations, we can do all the tricks that we've learned to do. In particular, we can use Euler to simulate them. So that's something that they do in this paper a lot. So you can, if you don't know what the analytical solution is, and in this case, with the function f that we had, that nonlinearity, the analytical solution doesn't exist, so nobody knows. So you need to run the simulations, but you want to know what happens as a function of your parameters. You can run simulations. And also, you can look at the fixed points, you can linearize them, you can try to understand what's going on there. So let's do that. And we'll do it. Oops, that's not. So here I'm showing you, this is our variable x. Everything is bounded between 0 and 1. Over here, the label is gone. Over here is our variable y. So the y-axis stands for the activity of y. And the blue line are the red line, and the red line are the null clients that Stephen talked about. So let me change some of the parameters. We've got an input to unit x and an input to unit y. It turns out that it simplified things a little bit here. If I divided that into common input, so this is input that's common to both the x and the y unit, and this is an asymmetric input, but from these you can find ix and iy. And right now the asymmetric input is set to 0, so all I did was increase the common input a little bit. And what you can see is that if there's very little input to both neurons, if there's very little excitation, then the circuit doesn't do anything, right? There's nothing driving it. And we can see that, if you can see the averages, you can see they're all coming down here. There's a single fixed point, and it turns out to be a stable one. Up over here, what we can do is we find the fixed point, we linearize around that fixed point. I was too lazy to actually write down the equations and do all the calculus to linearize. So instead, having found the fixed point, I just estimated the linear matrix numerically. Right? I have a function that tells me what x dot is, and I just evaluate that at x dot as a function of x dot as a function of x plus a little step. I take the difference, divide by the little step. That's an estimate. That's the first order estimate of the derivative of x dot. Right? And the derivative of x dot, the partial derivative of x dot with respect to x, with respect to the y, and the partial derivative of y dot with respect to x and with respect to y. That was the Jacobian. That was the matrix that told us what are the linear dynamics around this fixed point. So I was too lazy to do the calculus. I did that because that takes only a few lines. And then over here, I take that matrix and I toss it at Julia and I ask, what are the eigenvalues? And that's what you're seeing here. So 2 negative eigenvalues, what does that tell you about the fixed point? Yes, stable indeed, which is what you can see from the arrows. Okay, and it kind of makes sense, right? There's hardly any input to the circuit. It's not going to do anything. The firing rates of both neurons, I'm calling them neurons, but really they represent populations. The activity of both populations just goes to 0 because there's nothing tickling the circuit into doing it. So let's drive it, right? So let's add some excitation, which is this parameter. Let's just make that climb. And as you make it climb, the null clients climb. And now you can see that we've gone through a bifurcation. So let me do that again. Let's do the bifurcation. Bifurcations, you remember, are when fixed points appear or disappear. Here, wherever the two null clients cross, that's a fixed point, because the blue one is y dot equals 0, the red one is x dot equals 0. When they cross, both x dot and y dot are 0, so that's a fixed point. And as we change this, you'll see that kind of like right around here, now they start crossing in a bunch of points. It's almost like a continuum. And if you looked really closely, you would see that instead of one crossing point, now you have 3 crossing points. And so where those new fixed points appeared, that was a bifurcation. The nature of the dynamics changes. And now, really, if we want to ask about everything, we want to know about, what's the linearized dynamics around here, and around here. I'm only showing you the eigenvalues for the linearized dynamics around the fixed point that's nearest to the middle. And now you can see that it has 1 positive eigenvalue and 1 negative eigenvalue. What does that mean? Saddle point, exactly. Saddle points are unstable, so it's an unstable saddle point. And if we have an unstable saddle point, what's your guess as to the nature of the other 2 fixed points? Stable or unstable? Here's the thing. Activity is bounded between 0 and 1. It's not linear dynamics. You can't fly off to infinity. And we know for sure that we're moving away from the center one, right? Because it's unstable. So what's going on with the other 2? Yeah, they have to be stable, right? If there's stuff flowing out of here and stuff flowing out of here, it's got to go somewhere. So actually, when a stable point changes nature, and you don't have imaginary eigenvalues, if it was stable and becomes unstable, now 2 stable fixed points are born. That's called a pitchfork bifurcation, and I think maybe we had one. No, I guess we didn't have it in the notes. Anyway, another name for a bifurcation, but it's a bifurcation. And this bifurcation, once we're in that regime, that's the key kind of decision-making dynamics regime. Because now this means that whatever the system does is going to either end up here at this stable point or end up here. What are those 2 stable points? This one is x is very active and y is inactive, whereas the one on the upper left is y is very active and x is at 0. Those are the 2 decisions, okay? Or the 2 outcomes of the decisions. Okay, so we've got a system that we'll start it, right? So the stimulus will be to provide some input to the system, and the system itself will go to one of 2 options necessarily. That's a kind of decision. So how do we get the system to go? So let me change one parameter over here. Here we go. Let's make this 80. Yeah. Failure of the system. And try again. Actually, do this. Bear with me. Okay, it's looking a little better. We're almost there. Okay, now it's good. So we're starting from, the idea in this paper is, imagine that before the stimulus comes on, that this common input is really low. Then the system is at this single stable point. And I'm showing you a bunch of dots. I'm showing you 80 dots. So imagine that as if it were 80 trials. Each dot represents kind of like what the state of the system in one trial. Okay? And in addition, I'm adding a bunch of noise, partly because, well, when we put electrodes in, there's stuff that happens that we can't account for, so we call it noise. So models like this often have a noise parameter. Also, we know that sensory systems are noisy. That we do know for a fact. So it's not unreasonable to add a little bit of noise. So the little bit of noise is what is making all of these kind of like jiggle around. And then the idea is the stimulus comes in. Now you increase that common input. Now the system goes into its what's called bistable dynamics. There's the unstable fixed point in the middle, and the two stable fixed points on the sides. And so the system goes off towards one of the two decisions. And in this case, everything so far has been symmetric. The inputs to the two nodes were exactly symmetric. So what you see is that on half the trials, it went one way, and on the other half of the trials, it went the other way. And so what does this correspond to? This corresponds in the model to the idea of, oh, if you actually have a 0% coherence stimulus, there's no asymmetry in the stimulus. But you have to decide either right or left, then on average, half the time you're going to decide right and half the time you're going to decide left. It turns out that subjects, including monkeys and rats and mice, have like particular biases. So some people like to respond right. So when there's no input, there will be a bias. But if you train that out and you balance things out, you'll get something like this. So how do we get something that we do get a difference in terms of a stimulus? So now imagine that coherence value, right? We said that the coherence could go from 0% to 100%, no stimulus at all, to super strong stimulus. And in addition, you can do that for motion going to the right, or you could do it for motion going to the left. Right? So we could imagine that our stimulus input is something that could range from minus 100 full strong motion to the left to plus 100 full strong motion to the right. What could we do in the model that would have that kind of flavor? So we're trying to make a mapping between variables in the world, behavior, stimuli with experimental subjects. You know, it could be you sitting in a booth and doing this task, and variables in the model. So if you think of the variables that we have in the model, here, I have some notes, but I'll draw a kind of like graphical representation again. Where are points where we can have some asymmetry? Right? Because say that you're doing a trial where the coherence was minus 30%, that means the leftwards 30% coherence, that's asymmetric. Left and right were not identical. Right? So we have to put in something that kind of looks like that here. So what variables might be changed here that would seem not crazy to change? For example, things that we could change. We had our equations, which were x dot is minus x plus f I sub x plus w plus x plus w y is minus y Same thing, just swapping x and y. And we could say, oh, I know what. I'm going to make the function f for one node different to the function f for the other node. Yeah, maybe. Now, supposedly those functions were about the biophysical properties of those neurons. So that might be a funny thing to do.
So it's representing two different decision-making possibilities.
So the outcome is what represents them. Right? So this is just the activities of two populations of neurons. What the value of those activities are, that's what tells you what the decision was. And you can see in these dynamics, because this point is unstable, and this is stable, and this is stable, the system necessarily will end up either here or here. Which one of the two it ends up, that's the decision. That's how you read out the decision.
50% because it's symmetric with the babies.
Yeah, if everything is symmetric, then things are going to end up going 50-50. So let's run it again. So I turned off the input. So now again we have the single fixed point in the middle, and it's stable, so everything goes back there. And I forgot to write code that erases the tails. Never mind. But let's turn the input up again. That would be the stimulus came on. The stimulus is at 0% coherence, so it's symmetric. On roughly half of the trials, it ended up here. That was, let's call this go left. On the other half, it ended up here. Let's call this go right. But now, go ahead.
Is the amount of input that you get to a single neuron indicative of which decision or which output? Like, so if you take the IY from the Y neuron, would that affect?
Well, in a way, the model is there for us to play with. Right? So you're asking, is it indicative of something? We can choose to make it indicative. So the inputs, do they tell us what the outcome of the decision is? Well, that would be a little funny because they're supposed to be the inputs to the system, right? We want to read, the system is going to do something, it's going to decide, and so we want to read the outcome of that as what the decision was. So that's why we're reading the activities, the value, the final value of x and y, that's what we're reading as the output of the system. But the input to the system, the subject has an input. Right? The subject has a visual stimulus. That's the input to the subject. So we could say, let's say that this represents the visual stimulus. And let's make asymmetries between x and y corresponds to the coherence. So let's say that x represents left, and y represents go right. So you could say, if you have leftward coherence, let's make this input a little bit bigger than that. And supposedly that should lead to an asymmetry in the results. Let's try it. Let's see what happens. So let's make it slightly asymmetric. I forget which way the sign of the asymmetry goes. Let me make that a little bigger. And let's pump up the input and see what happens. It is slightly asymmetric, right? You guys see that? Maybe I should make the asymmetry bigger. Let's start again. Off we go. Yeah, this time they mostly end up over here. Right? So why does that happen? What's going on is that we're starting kind of on the diagonal. Right? The fixed point is close to the 0, 0 point. And then as we change the asymmetry, the nullines change asymmetrically. So for example, if we add a lot of input to x, then its nullline is going to move up and down, whereas the other one is going to move rightwards and leftwards. So I hope you can see the blue nullline, that's the y dot, moving kind of like to the left and to the right, and the x nullline moving up and down. And as you do that, if one of them moves one way and the other moves the other, then this unstable point is no longer on the 45-degree line. It's to one side of it. Right? And that unstable point, that's the point which cleaves everything into, as you start from the center, are you going to go this way or are you going to go that way? So as you move the unstable point, you're moving the fraction of trajectories that end up on one side or another. And you can move that gradually, right? So you remember that I said, oh, there's a psychometric plot where if we plot the fraction of correct responses as a function of the coherence, something smooth. Well, we can also move our asymmetry smoothly. So for example, if I put it over here, so the asymmetries say anything to the right of 0, the red line is 0, represents the correct decision would be x is very active. So if I make that asymmetry very strong, then almost all of them, or in this case, all 80 trajectories ended up on one side. But as I make the asymmetry weaker, then the fraction of trajectories that end on one side is going to change gradually. Whoa, still all of them. Okay, maybe I should have used more dots or made it even weaker. But you can titrate. Because the asymmetry is an analog number, you can titrate that, right? And so we're going to be able to get a smooth curve that looks like this. Now, how do we get reaction times out of this? Any thoughts for that? Like in this picture, what corresponds to reaction time? So remember, each dot is one trial, right? And as the system is moving through space, that's your brain thinking, or at least that's what the model is trying to convince us of. Right? So say as the dot moves around here, when it's here, could we say that the decision is made? When it's here, is the decision made? When it's here, is the decision made? How do we tell when the decision is made? It's a model. It's for us to play with. You're free to invent whatever you want. After you invent something, then we start asking, well, is this plausible? Can we see how that would match biology? What it would correspond to in biology? But the first step is just to try and think of something. So if I told you, in this network, in this little circuit, this 2-node circuit, I'm going to read off what the decisions are. Or actually, I didn't tell you that. I told you, I'm going to ask you to read off what the decisions are. How would you read off a decision, and when would you do it? Take a guess. Any suggestion is valid.
The one with the most points after the ball, correct?
So the one with the most points, each point is a trial. So how would you read off the decision on one trial?
One each point gets to one.
Okay. So you could say, which of the two fixed points it gets to, that's the outcome of the decision. But when does it get there? As you approach a fixed point, when do you get exactly to the fixed point? Say in linear dynamics. Yeah, because you approach it exponentially, right? So asymptotically, you reach the fixed point. But it takes forever. So we can't say when you reach the fixed point exactly. We have to choose something. So I made something up in that spirit. Right? I'm literally making something up. I said, you know what? When one of the two units has activity that's greater than this, I'm going to say, that's it. The decision is done. Right? And if we place that threshold kind of reasonably close to the fixed point, it's not crazy. And we could imagine that this is the circuit where the decision is made, and a downstream circuit is waiting for activity to reach a certain amount, and once the activity reaches a certain amount, that's when you move your hand or move your eyes. So we can make up a biological correspondence story. So let's run it like that. And what I'm doing, once I've lowered the threshold, you'll see what the point of these axes here and here were. And the point of those axes is that they're showing you a histogram of the reaction times. Okay? So we have 80 trials all going at once on the screen in parallel. And when each one hits one of these gray boundaries, these thresholds, that's going to correspond to the, oh, that's the moment in which the decision happened. So let's run the decision again. Start all the way from here. So everything's at 0, 0. Now off we go. You can see the histogram building up. Oh, really, I should restart it because T is at 400 seconds, so that's very confusing. Let me restart the system. So this is the histogram of reaction times when the subject decided this, decision 1, and these are the reaction times when the subject decided the other decision. And what I want you to notice is that these have lower numbers than these. So it turns out that in this system, correct decisions are faster than incorrect decisions. And that's something that's seen in the data itself. Now, another thing I want to point out. This unstable point, the fixed point in the middle, how fast do we move away from it? So suppose that we have very low noise. If we have very, very low noise, and in fact, let's make the asymmetry, keep things symmetric. If you're exactly at the fixed point, you don't move away from it. It's only the noise that is moving us away from the fixed point. So how fast do we move away? Let me try again with noise of 0 and see if I got all my... Any little asymmetry is going to screw it up. But, okay, so there was a little asymmetry left in the sliders. What governs how fast we move away? So, in terms of the linearized dynamics, once we linearize the dynamics, we've understood the dynamics around this unstable point. And so what are the things that characterize, if you have linear dynamics, you know that the solutions are going to look like in each of the eigendirections. And so how fast or how quickly do you move? In this function, what determines fast or slow? Exactly. It's the eigenvalue that tells you you're scaling with respect to time. If the eigenvalue is really small, that means that even if time changes by a lot of seconds, there wasn't a lot of change here, so you're moving slowly. If the eigenvalue is really large, you move fast. If the eigenvalue is large and negative, you move into the fixed point really fast. The negative eigenvalue corresponds to this direction along the main diagonal. Right? That's when you're moving in. The negative eigenvalue. The positive eigenvalue, this one, corresponds to this direction. And that one is telling you how fast you move up. What happens after you move up? So suppose that you're trying to deliberate on this decision. My system is frozen. I don't know why. Come back. Come back. It's alive. Suppose that you've got a perfectly neutral decision. So that means that the evidence for left and the evidence for right are perfectly balanced. And that's what I tried to do here. Right? So I tried to set the asymmetry to 0. If you go back to that accumulator story that I told at the beginning, I said, well, you're accumulating evidence, and you're going to ask which side of the boundary you're on. But if the evidence that you're accumulating is perfectly balanced, you would never move far enough from the decision boundary to say, oh, I commit to a decision. Is this system capable of that? Is this system capable of, a very long time of accumulating information? If the information is balanced, it keeps deliberating, it keeps making up its mind. With the parameters as I have them right now, could the system do it? So what would that mean? Going off towards one of the two fixed points, that means you've decided, right? You're heading towards a fixed point. So keeping deliberating corresponds to staying close to the unstable fixed point. Because that's where, if enough stuff comes that pushes you the other way, you might go over the hump and head off in the other direction. So if there's a little bit of noise over here, but there's enough evidence pulling you that way, if you're close to the fixed point, you might still end up going that way. So the deliberation time corresponds to how long you can stay close to that unstable fixed point. And what controls that? In terms of the things that we talk about in class, in terms of the things that I have written on the board, it's the positive eigenvalue. So as we play with the parameters, for this system, if we want to ask how long can we deliberate for, it's this positive eigenvalue that is going to tell you. Yeah?
In this system, once you start moving away from the system, there's nothing bring you back.
Well, it would have to be a very strong force that brought you back. Or, there is noise. If there's a very fortuitous sequence of noise, it might push you back. But yeah, if things were perfectly noiseless, then once you start going in one direction, yeah, there's no coming back.
The decision is made quickly.
Yeah, so then you could say that the decision is made already. Exactly. So this aspect of, there's a finite time to how long the system can stay near the unstable point, that's what corresponds to, there was a slide where I said, the subjects weight the early part of the stimulus more than the later part. That's the time scale that people are trying to match here. Right? Because experimentally it seemed like, people could only deliberate for about 500 milliseconds, so we'd like to set up our system so that this eigenvalue, in fact, 1 over that eigenvalue corresponded to about 500 milliseconds. Because you can write e to the lambda t as e to the t over 1 over lambda. And the only reason I'm writing it like that is that then this has units of seconds, and 1 over lambda has units of seconds, so we can think of it in terms of seconds. So if you want 500 milliseconds here, you want 1 over lambda to be 500 milliseconds. So there's other parameters that we can play with that we haven't gone. The self-excitation. There's fun things that does, but the basic properties of the system we've already seen. In the sense that you start with a single fixed point. That's where you haven't decided anything, you don't know anything. And then you increase the excitation to go through a bifurcation. You're going to a bistable system. A bistable system, that's the basic kind of system where you want to end up in either one of the stable states or the other. That's the basic kind of dynamics that you use for decision making. Now, one of the things that I pointed out is that for any particular value of asymmetry and noise, for any particular value of the parameters, you end up with a fraction of trials where the decision ended up going one way, and also a distribution of reaction times. So if you ran this an infinite number of times, you could ask, for these parameters, for these values of the parameters, what's the probability that the system will make one of the choices as opposed to the other? And what's the probability that the system will do so with a particular reaction time? And what are the parameters that go into that? All of the parameters that we've got on the screen. The threshold affects the reaction times. The amount of noise is going to affect the proportion of choices. All of the parameters that we have here, the strength of the inputs, the strength of the weights, all of those. And so whenever you're dealing with a model like this and you want to compare it to experimental data, you want to ask, how do I set my parameter values so as to best match the experimental data? That's the kind of thing that you could do with a model like this, and that, in fact, people do with models like this or more complicated models too. So if we run the model many times, what we're going to be able to do is say, for a particular value of the parameters, and I'm going to summarize the parameters as one vector of parameters theta, I have probabilities for observing certain outcomes, the reaction time and the choice. So given those parameters, I could write down what's the probability of seeing the data that I actually saw, given the parameters. So how do I choose my parameter values? Well, one kind of intuitive thing to do would be to say, let me choose the parameter values that would maximize that probability. This is called the likelihood of the data. And finding the parameters that maximize the likelihood is called the maximum likelihood procedure. And it feels like an intuitive thing to do. Bear with me a second while I turn this off. It turns out to correspond to also something else, something that's called maximum a posteriori. And the things that we're building up towards to in the last two classes are going to be doing this kind of model field. And like I said, we haven't yet figured out what the final assignment is going to be, but we're going to try and make it fun, and we're going to try and get you guys to fit the models, and we'll give you the code to do that. So these are the kind of procedures we're going to be going through. To look at maximum a posteriori, we need to know about Bayes' rule. How many people have not gone through Bayes' rule, or let me phrase it differently. How many people have only a vague recollection of Bayes' rule? Okay. Very worth going through. So maybe I'll get back to the model, but if not, we will have time. We just have time to do Bayes' rule. Super important and relatively simple. So probabilities are defined by two things. If you have a set of outcomes x, or maybe I'll call them xi, where I indexes the different outcomes, the probability of a particular outcome is approximately the fraction of times that you'd see that outcome if you repeated your experiment an infinite number of times. The classic example, of course, is a coin. You know, what fraction of times do you see heads? About half the time. So the probability of seeing heads is a half. And if you think of all the possible outcomes that could happen, well, all those fractions have to add up to 1, right? Because if you've thought of all the outcomes that could happen, that's the entire universe. There are no fractions outside that. So that tells you that the sum over all possible outcomes of P of x has to be equal to 1. And a fraction, the fraction of times you get an outcome, that's an inherently positive number, right? You're not going to get a negative fraction of times that you get heads. So for all outcomes, their probability has to be bigger or equal to 0. And those two things, if you've got a function p that has these two properties, then that's a probability. Those are the two key things that define a probability. Now let's suppose that on each trial of an experiment, instead of having one thing that can happen, you have two things that can happen. So let's say, let's say that you're going to have two outcomes on each trial. And those are that you've got two things, x and y, that can happen. And x is either going to be A or B, and y is either going to be 1, 2, or 3. So say on one trial you might get 1A, on a different trial you might get 3B, and so on and so forth. So the universe of things that can happen are 6, right? There's 1A, 1B, 2A, 2B, 3A, 3B. So let's just write those out. A, B, 1, 2, 3. Right, so this is x and this is y. So those 6 possibilities, that's our universe. So each one of those possibilities has some probability of happening, and those probabilities have to add up to 1. And for different things, the numbers could be different, right? As long as they satisfy those two properties, we've got a proper probability distribution, everything's well defined. So let's say that the probabilities for each of these 6 looked like this. I could ask you, what's the probability of getting a 1, of y equals 1? Where you're going to get a y equals 1 if you get 1a, or if you get 1b, and you get 1a a quarter of the time, and you get 1b a quarter of the time. So the probability of getting a 1, independently of whether x was a or b, is a half. These are called the marginal probabilities. You've got 2 possible outcomes, but you're only asking about 1. And to get that, you sum across the other outcome. So if we sum horizontally along here, a quarter per a quarter, that's a half. The probability of getting a 2 is not a half, it's an eighth. The probability of getting a 3 is 3/8. The probability of getting A is 5/8. And now I'm summing vertically. And the probability of getting B is 3/8. So for example, the probability of getting a 2, independently of whether you also got an A or a B in that trial, that is 1/8. We're reading that off right here. But now, suppose I asked you, what's the probability of getting a 2 given that you got a B on that same trial? What do you guys think? What would be your answer? 0, right? Because when we say, oh, given that you've got a B, what you're saying is that now your universe is here. It's no longer the full universe, right? If you know that you got a B, you know that the chance of getting a 2 is 0. How about if I said, what's the probability of getting an what's the probability of getting a 2 if you know for sure that you got an A, given that you got an A? What would you say to that? You might be tempted to read it off and say 1/8, but that wouldn't be quite right, because now the universe of possibilities is here, right? I've told you, given that you got an A, you already know that you got an A. So out of all of these possibilities, what fraction of them is a 2? Well, let's just write it out. So it's going to be 1/8, right? So that's the thing in the middle, this, divided by the total. So it's 1/8 over 1/4 plus 1/8 plus 1/4. That's the fraction of times out of these that you landed here. Does that seem intuitive and reasonable? Okay, so what is it that we wrote down? The 1/8, that's the probability of getting a 1, sorry, not 1. That's the probability of getting a 2 and an A. And the thing that we wrote in the denominator, this sum, that's the overall probability of getting an A, right? So we just wrote down Bayes' rule. That is Bayes' rule. You can derive Bayes' rule anytime you like, just kind of thinking through this, the universe of possibilities, right? So what we said was the probability of getting some value for y, given that you know x, was the probability of seeing that y and that x divided by the probability of x. That's Bayes' rule. And Bayes' rule is just a way of keeping your universe straight, right? Keeping your sums to 1. Why does it matter like heck to us? Well, where we're most going to use it, and I'll just write it down and then we'll stop, is that in the model that we wrote down, we know how to get the probability of the data given the parameters. But maybe what we'd really like is the probability of the parameters given the data. That's what you really want to find out, right? Given some experimental data, what's the most likely parameters? What are the possibilities for my parameters? This is the question that we're trying to ask. And Bayes' rule tells us what the answer is. And in fact, it tells us that it's proportional to that likelihood. So we'll come back to this thing on the top next lecture. But the important thing to remember is Bayes' rule. If you forget all the modeling, remember Bayes' rule, because that one is really important.
The time for the extra study session, I put up a call